Hi guys, here I will be going through Unit 9 practice test. So the first one is talking about collision theory. So we need to know, what does it take to have effective collisions? It doesn't have to do with their masses, density. So we know that we talked about you have to have the right amount of the energy and be at the right orientation. Number 2, why does increasing the temperature increase the rate? Well, remember, temperature is a measure of average kinetic energy. If we increase the temperature, we increase the kinetic energy. So can't be A or B. And the reason why the rate is going to increase is because they're going to collide more frequently. 3, if we have gaseous reactants and we increase the pressure, we need to think about how if we increase pressure, it'd be as if we decrease volume. So we're not going to worry about volume. So if we have a box with a few molecules, increasing pressure would be as if we put them in a smaller box. So it's as if we put or increased the concentration, C. We should know as we increase the concentration, our rate increases. That is the definition, B, because it's more likely that there will be more collisions. 5, adding a catalyst. So what does this do? Well, it lowers the activation energy. This is why we are able to speed up things using catalysts. So we can't be A or C. And so what happens is that they end up taking alternate reaction pathway. So if we kept the same pathway, nothing would change. So B is our answer. Number 6. So this says compared to the rate of inorganic reactions, the rate of organic reactions generally. So you may be thinking we didn't talk about inorganic versus organic. But if we dive deeper into the answers, we start talking about covalent bonds. We didn't spend time really talking about ions, but when we talked about covalent bonds, it was in the sense of covalent versus ionic, where we said covalent tend to have slow reaction rates where ionic are fast. So thinking about that, because organic particles contain covalent bonds, they're going to be slower. So it can't be D. Number 7. Based on the nature of reactants in each of the equations below, which reaction at 25 degrees Celsius will occur at the fastest rate? This question also has to do with that covalent versus ionic. So I want to remind you guys, covalent molecules are nonmetal, nonmetal. Ionic, they contain metals. So when you think of the periodic table, I'm just going to draw some generic little table here. There, over on the right-hand side, the upper right corner, this is where the nonmetals live. So if you have anything that is over in this side of the table except hydrogen, that's a nonmetal, it's going to be ionic. So we see things like first group metals like sodium, calcium is second group. So we know for sure that these contain ionic compounds. If you see tons of carbons, hydrogens, oxygens, that screams covalent. And the nice thing, if you think about the first 2 letters of covalent, they're C and O. So think of that carbon, oxygen, that side of the periodic table are covalent. Now, when we're left deciding between B and D, the key here is that yes, we have an ionic solid, but in this equation, they're already dissolved in water. So you have to remember the definition of AQ means dissolved in water. And we talked about dissolving ionic compounds in water acts as a catalyst. So this one will react at the quickest rate. All right, moving on to the next page here. We need to find a reaction order, or look at how a reaction order is found. And so to find one, what kind of ratios do we set up? Well, this is when we set up the concentration of A over A to some power. That N, this is the reaction order. So it's saying, how do we find that? Well, the rate ratio, it says that we have a rate ratio. What is this equal to? Well, we don't compare temperatures, time, or pressure, but it's the concentration ratio. Number 9. So I'm going to erase this to give myself some more space. This wants you to find the rate law for this reaction. So on the key posted, it did have the wrong answer, so don't worry if you were freaking out. But how we would find it is we need to split it into both reactants here and solve for their reaction order. So I'm going to start with NH4+. Now, feel free to just call this one A and call this one B for less writing, but I'm just going to continue writing with the full compound. So when I go to find the reaction order for this, I know that I'm going to put some sort of NH4+ concentration over another, so I'm going to have to pick two different trials. The key here when I pick trials is making sure that the concentration of the other compound stays the same. So I'm going to pick 1 and 2. Now, when deciding which one to put on top of the other, I look at what's bigger. The concentration of trial 2 has a larger value than 1, so I'm going to put T2 over T1 and set that equal to the rates from T2 over T1, which are 0.030 over 0.020. If you simplify this, you would get that. Oh, sorry, I'll plug in the concentrations here for NH4. So you'd have 0.015 over 0.1010. So some power of n is equal to 0.030 over 0.020. Simplifying this, you get that 1.5, n is equal to 1.5. So n must be equal to 1. So we know that the reaction order for NH4+ is 1. If you want to go in and cancel out C and B right away, you can, because those are second order. We know that can't be possible. Now, solving for the other one, we need to find two trials that NH4 stays the same. If you look, that would be 1 and 3. And the concentration of 1 is higher than 3, so I'm going to put T1 over T3. So I have 0.020 over 0.010. M is equal to 0.020 over 0.005. If you simplify, you get that 2 to the power of m is equal to 4. So our m must be 2. The only one that fits that is D. So our answer is D for number 9. 10. So for 10, it wants to know the units. I'm going to keep using this space up here, so I'm going to erase this work. And I'm going to put the work for number 10 up here. What are the units of K for this rate law? Now, in order to figure that out, you need to know a few things. Rate, I'm going to write this equation up here. Rate always has the same units. It's always moles over liters times some unit of time. If you look at 10, the unit of time they're talking about is seconds. So this will always be the format for rate. We want to figure out what K is. Units of concentration will always be moles over liter. So I'm filling those in, not forgetting that we're squaring B. So if I simplify the right-hand side first, we get that moles over liter times second is equal to moles cubed over liters times reaction K's units. Now, when you divide by a fraction, you multiply by the reciprocal, and so this is when I say don't cry, flip and multiply. So what you're getting, I forgot to put a cube there, is moles over liter times second multiplied by liters cubed over moles cubed. That is equal to the units of K. 1 moles per liter cancels out with one of the moles per liters on the other side. So we're going to change these to the powers of 2 so that you get that your units are D. So make sure that you know when you see negative exponents, it just means it's in the denominator. So liters squared over moles squared times second is the same thing as what's shown in your answer there. Number 11 had a typo. This equal sign should be a plus sign. Now, reading the problem, it says that this reaction is first order with respect to reactant A and second to B. So the first thing you have to be able to pull from this question is if we're thinking about rate is equal to K times the concentration of A times the concentration of B. When it tells you it's first order with respect to A, that means this is power of 1. So the orders are the exponents. Second order then will be 2 as your exponent. Now, it's saying what will happen if reactant A is doubled and the concentration of B is halved. So the rate constant K, it's a constant. So we don't really have to consider that so much, but we want to see what happens if we double A and half B. So what will happen to our rate? I'm just going to ignore K for now. Like I said, it's a constant. And I'm literally just going to put in a 2 for A and a half for B. If we simplify that, we get 2 times 1/4. Well, 2 times a fourth is 2 over 4 or 1/2. So the rate will be halved or decreased by a factor of 2. All right, number 12 here. Given this equilibrium, which statement describes the system? So it doesn't matter what type of equation I put. I could put any equilibrium equation here. The key is knowing the definitions of equilibrium. Concentrations are constant. They do not have to be equal, so it couldn't be C, and these ones talk about them changing. The definition of that equilibrium is when your concentrations are constant. All right, 13. So 13 talks about equilibrium between a phase change. So I can write this equation as such. So this is kind of what we're looking at, this type of equilibrium. Again, this is a definition question. We didn't talk about how equilibrium affects the mass or volume, or the moles. And so if this question even talked about different rates, the key here is that what we talked about for equilibrium is that the forward rate is equal to the reverse rate, which is exactly what this is talking about. When liquid goes to gas, which is the evaporation of H2O, in what I wrote here, that would be the reverse, is equal to the rate of condensation of H2O going from gas to liquid, which is the forward. All right, 14. So this section is heavily on definitions here. So this graph is of an equilibrium, and here it says if the graph of the reaction at equilibrium is at equilibrium after 60 seconds, which this is where 60 seconds occurs, what happens to the concentrations? So you didn't even really need to know that the concentrations are constant. You should, but that is what it's telling us is, okay, yeah, we know it's at equilibrium because that's when they become constant. When the rate of forward equals the rate of reverse. Which changes can reach dynamic equilibrium? Well, here, we didn't talk about nuclear changes, so that's a big red flag. But we talked about both in a chemical and a physical sense. So chemical is like reactions when they're changing. Physical would be like this top problem here when we went from a phase change. So equilibrium can happen between chemical and physical changes. All right, on to the next page. So this one, we didn't really cover this one. It's a little, I guess, in depth. But pretty much, when you have a double replacement reaction, we didn't talk about them in the sense of equilibrium because they're not going to reach equilibrium. When you have two ionic solids, they go to completion because a precipitate is formed that does not go back into solution. So these are very much a one-sided arrow. You will not see that double replacement have that double-sided arrow because that precipitate is happy. It wants to be there and it will not go back into solution. All right, number 17. What is the correct equilibrium expression? So this is working on writing mass action or equilibrium expressions. So it's always products over reactants. In our case, we have that CO2 as our product, so we know that we want the concentration of CO2. We use that coefficient as the power. That's the only product and then we'd put that over CO, which has a 2, so power of 2 times O2's concentration. And so the correct answer here will be B. Now, 18 and 19 talk about those values for KEQ. The biggest thing that I want you guys to know is the larger the KEQ, this would be more products favored. Because if you think about what KEQ is, it's the ratio of products over reactants. So the more we increase the numerator, the larger the number we'll get. So, which will go almost to completion? That's just what's the largest number. That's going to be D. Because remember, negative exponents are getting smaller. 19 says, which favors the formation of AB? Well, you'd have to recognize that AB is our product. So again, which has the highest value? Now, these are all negative exponents, so you want to find the smallest negative exponent. That would be A. That is the largest value. 20. So given this reaction, when the reaction is subjected to stress, what will happen? So what happens to the concentration when you stress a system out? It affects the whole entire thing. So it's not just reactants, it's not just products. A whole change will happen across the whole system. So it will be both reactants and products. So looking at this equation, which will affect an increase of pressure, or what effect will an increase of pressure have? So we know for sure we have gases, so this will have an effect. If they weren't gases, nothing would happen. Now, an easy way to look is think about your initial concentration. You have 2 moles of gas on this side, and you have 4 moles of gas on this one. What's going to happen if we increase the pressure is we're going to shift to the side with less moles. So we're going to shift right, which will be an increase of NH3, and therefore decrease the amount of N2. 22. What will happen if a catalyst is added? So, catalysts do not affect anything but activation, their activation energy, therefore rates. So it can't be concentrations. And if we're affecting rates, it has to be the one talking about rates here. Because if we change the forward and reverse reactions, we are speeding up the forward and the reverse in an equal manner. 23. What occurs when the concentration of H2 is increased? So that's when we think about if we increase this side, that would push our teeter-totter up and our ball would roll to the right. So answer A. The rate of forward reaction increases and the concentration of N2 will therefore decrease. Given this system, what if we increase the temperature? So here would be putting an up arrow with the energy term. Again, we are pushing our system to the right, and so the concentration of NO2 will therefore increase because that's a product. D. Which change occurs when KBr is dissolved? So, do we have any potassium ions? No, doesn't matter. Do we have bromine ions? Yes. So if we add KBr, we are increasing bromine concentration, which will therefore shift to the left, and the concentration of Ag plus will decrease because it's on the same side as where we are adding our product. Last one here. So this will be very similar to what you guys are expected to do for the only not multiple choice questions on your test. So it wants us to find the rate law expression including K. So first step with this is figuring out the orders in respect to reactant A and B. So I'm going to start with A. Now when I think of concentrations for A, I'm going to want to make sure to pick trials where B is constant. So I'm going to pick trials 1 and 2. So I am also going to put rate 2 over rate 1 because the concentration of A at trial 2 is bigger than trial 1. So if we plug in our numbers, we get 0.3 0.300 over 0.100 to some power of n is equal to 2.457 over 0.273. If you simplify that, you get that 3 to some power of n is equal to 9. Now you may be wanting to throw a 3 as an exponent because you think 3 times 3 is 9, but don't forget exponents are how many times you multiply that thing by itself. So 3 times 3 would actually be n is equal to 2. For reaction order of B, set this up here. The ones I'm going to select for B are where A stays constant, so I'm going to do trials 1 and 3, but T3 has a higher concentration than T1, so I'll make sure to put that on top, just to make sure my math is a little bit simpler. Plug those things in, we get 0.200 is over 0.100 to some power of m, and that is equal to 0.272 over 0.273. Simplifying this, you get that 2m is equal to 1. Now, you may have gotten like 0.999 or something. Just route it to 1. This is very similar to what you would actually see in real life, is that, yeah, your rates may not be exactly the same, but they're about the same. So the factor would be 1 in this case. The only number that can change a number that's not 1 to 1 is 0. So the power has to be 0. So when you write this initial rate expression, you'd get that rate is equal to k times a to the power of 2 b to the 0 power. So we don't even really need this term as we continue on to figure out k. So I'm going to move up to the top so I can see the values that I'm plugging in. So solving for k, I get that k is equal to rate divided by the concentration of A squared, because we don't have to consider B because it's 0 order. I'm going to plug in the information from trial 1. That means k is equal to 0.273 divided by 0.100 squared. K is equal to 27.3. And now, for units, I'm going to show you guys how I'm going to solve for units here. If we have that our rate is in units of moles over liters times second, and we're dividing that by moles over liters squared, don't cry, flip and multiply. We have moles over liters times second multiplied by liters squared over moles squared. One of these squares cancels out with the moles and liters on the other side, and so you get units of liters over moles times second. Then the problem would be done.